For our next tutorial, we're going to explore a new data set, this time about crops. So in this tutorial, we're going to learn about the impact of climate change on agriculture, and we're going to explore a data set about crops that is taken from a satellite, so a remote sensing data set. And we're going to see how logistic regression can be used to identify crops in this satellite data. We'll also learn about artificial neural networks and how those could also be used for this problem. And we're going to talk about the problem of overfitting in machine learning models. So now let's learn about how climate change is impacting agriculture and how we can see that through remote sensing of crops. So climate change will impact agriculture in a variety of ways. It actually already has begun impacting agriculture. And so this will occur through changes in the climate that will impact crop yields. So how much a plant is producing, how much edible food a plant is producing. When things like temperature and precipitation change, plants that were maybe well suited for a certain region will start to produce less, and so won't be able to provide as much food. The things like growing season will also change. So for what time period can you grow plants at a certain location? When should you plant them? When should you harvest them? Those things will also change. And a shorter growing season can mean fewer harvests. It can also mean lower yield. So growing season will be impacted by changes in climate. Also, growing regions will be impacted. Certain crops will no longer be growable in regions that they've been grown in for many, many years. And there may be new regions that become available for certain crops, but people will need to know to build those crops or plant those crops in those regions, which will be different than what has been done historically. So understanding how climate change will impact where things can grow, when they can grow, what can grow, is really important for planning agriculture and food production. So knowing all of this data, knowing accurate agricultural data is important for predicting food supply, being able to divert resources where they should go in order to keep food supply steady and keep everyone fed. It's also important for providing assistance to farmers. You need to know where farmers are and what they're growing and what they need in order to help them, in order to keep food supplies up. And so therefore, knowing where the farmers are and what they're growing is really important. And also in general, monitoring land use. So knowing how we use land is important for impacting climate change, and knowing what's agricultural land, which is versus what's natural land, that kind of thing is important for understanding impacts of climate change. So there are many different studies that use satellite imagery to monitor and understand crops or predict crop yield. Sentinel-2 is a particular satellite that can be used for this kind of thing. You may have encountered the details of these kinds of systems in your remote sensing lecture, but Sentinel-2 in particular has a 5-day revisit rate, so it goes to the same location every 5 days. It has between 10 and 60 meter spatial resolution, depending on which spectral band you're talking about, and it has 13 spectral bands in total. So you can get these nice images of different parts of the Earth from this Sentinel-2 satellite, and we can use that to identify what's happening on the land in those images. So the particular data set that we're working with, we're going to learn about that now, and it comes from Togo. So this is a region in Africa, a country in Africa, the Togolese Republic, and the data set that we have has for each location in the data set information from the Sentinel-2 satellite, along with information about crops that could be in that region. So this data set was originally documented in a study that was carried out by NASA and researchers at the University of Maryland. And the data for this tutorial was accessed through the crop harvest interface that's provided by NASA. So this is an interface where you can get access to many different remote sensing crop data sets. So the specific features of this data set. So as I said, for each location in Togo, we have a label as to whether that location contains crops or not. So is that location growing crops? Is it an area where agriculture is happening, or are there no crops growing in that location? And so we have that label for each data point, and then the features that we have from the Sentinel-2 satellite are all of the bands from Sentinel-2 except for B1 and B10. So these are all the spectral bands that Sentinel-2 has, and the different bands, as you learn about, have different kind of purposes. They contain different information. So B1, the coastal aerosol band, and B10, shortwave infrared, are considered more appropriate for studying clouds and aren't that helpful for understanding what's happening on the land. So those are not included in this data set. An additional thing that is included, in addition to each of the remaining bands, is the NDVI, which we also saw in our dengue fever data set, and you've seen before in the remote sensing tutorial. So this is the normalized difference vegetation index. Specifically, it's calculated through combining the B8 and B4 bands. So that's the near infrared and the red bands. And this, again, is a measure of vegetation, which you can imagine is very important if you're trying to detect crops. So the data set in total for each location gives you the value of the Sentinel-2 bands, with the exception of B1 and B10. And in addition, the NDVI is tacked on as well. So you get all of that information, and you're going to try to train the model to predict if there are crops or not in that location where those bands, that data is taken from. So the first thing you're going to do, as always, is just explore this data set, look at the distributions of the values, just make sure that you understand the basics of the data before you try to build a model. Then you're going to try to do binary classification on this data set using logistic regression. So as we learned about with logistic regression, you can classify data points as being in one category or another. Here, we obviously want to classify each data point as either containing crops or not containing crops. So this is a very straightforward binary classification. You either have crops at that location or you don't. And so the way that we can do this with logistic regression is, again, we will give the logistic regression model all of the bands and the NDVI as the regressors into the model. So those will be the X values. The thing we want to put out from the model is the label of crops or no crops. And so again, the way the logistic regression works is it has to learn these beta values for each of the input regressors. That gets passed through the sigmoidal function. And if it's above a threshold of 0.5, we'll say it's a crop. So the positive category, the 1 category is crop, the 0 category is no crop. So that's how we're going to map the labels onto values that the model can use to learn how to perform this binary classification problem. We're also going to evaluate this model, of course, to see how well it's performing. And we talked before about the concept of overall accuracy in binary classification and how that's one indication of how the model is performing, but it can be a little biased, especially if you have imbalanced data. It might not be the best way to evaluate your model. So you're also going to use precision and recall. These are two additional ways that you can evaluate a model that's doing binary classification. So what those metrics are, what they're based on, is this concept of true and false positives. So you can imagine that if you have a model and you have a data set, some points in your data do not contain the thing that you care about. So those are negatives. And so that's represented by the open circles here. So these would be the points that represent no crops. Some of the data points do have the thing of interest. So that would be the closed circles here, the filled in circles. Those would represent locations that do have crops. And so then you have a model that's going to try to identify the crops and no crops. And so when the model says that a location has a crop, and it in fact does, that's called a true positive. The model correctly identified that there's crop here. And so this circle represents all the data points that the model is saying has a crop in them. And so the model might also identify some locations as containing crops that don't. And so those would be false positives. So those are these open circles that are still in this larger circle. So those are errors that the model is making. So to understand the metrics of precision and recall, precision is a measure of how many of the points, in this case, how many of the locations that our model says contains crops, how many actually do. So that's the fraction of true positives over the sum of true and false positives. So what fraction of all the data points that the model says, yes, there's crops here, what fraction of those actually contain crops? Another metric is recall, and this is a measure of how many of the locations that actually contain crops does the model identify as containing crops. So here, the value on the bottom of this fraction is all of the locations that actually contain crops. And then the top of this fraction is the locations that the model identified as containing crops. So true positives over all of the actual positives in the data set. Okay, so those are two different metrics that can just give you a different sense of how the model is performing. In different problems, you might care about different errors more than others. So if you really want to make sure that you're finding all of the crops, then you care more about recall. If you want to make sure that everything that the model says that a crop really is one, then you care more about precision. So it's just important to think about in different real-world problems, different errors might matter more or less. And so by using different metrics, you can get a sense of what the model is doing and what it's doing right and what it's doing wrong. So when you're working with this data set, do think about the real world significance of the performance. In the paper where this data set was originally published, the authors actually used it to help in response to the COVID-19 pandemic. So at the start of the pandemic, the government of Togo was trying to prevent food shortages by distributing aid to farmers, but they didn't know where all the farmers were. They needed to be able to find where are people growing crops so that we can give them aid to help them in their agricultural needs and make sure that there aren't food shortages. And so by using recent remote sensing data and building a model that could classify crops, they were able to find the farmers in this region. And so you could imagine in this case, maybe the authors would care more about finding all of the farmers that exist. So they might care more about recall than about precision. Maybe they don't care. Sometimes it says that there are crops and they go to that location and there aren't, then fine, they won't distribute aid there, but they want to make sure that they're finding all the places that do. So that's a way in which the difference between precision and recall could have a real world impact and could matter. Okay, so after you train your logistic regression model and evaluate it on these metrics, you're going to try out artificial neural networks. Now, artificial neural networks are a very general purpose model that can be applied to a lot of different types of problems, a lot of different content problems. They've made progress recently on vision, language, recommendation systems. You've probably heard about artificial neural networks if you've heard about anything about AI in the news. They're very popular and they're a very general purpose, broad class of machine learning algorithm that can take on kind of many different forms. If you really want to learn more about them and go deep into this topic, then you should check out NeuroMatch's deep learning course. That's a course just like this one, but it's centered all around artificial neural network models. So for today, we're just going to get into the very basics and use it to build a very simple artificial neural network. So the base unit of an artificial neural network is an artificial neuron, as you can imagine. And so artificial neurons are very simple input-output devices, essentially. They take in a weighted sum of their inputs and they rectify it. What that means is that if the weighted sum is less than 0, it's set to 0, and if it's more than 0, it just stays what it is. So for example, let's say we have this artificial neuron, this blue circle here. It's getting input from either the data itself or from other artificial neurons, and that's represented by these blue values here. And each of those inputs has a weight to it, so that's represented by the numbers on these arrows. You would multiply all these values, 2 times 0, 1 times 0, negative 2 times 3, sum them up. Here you get negative 4. Because that's less than 0, the output of this model is simply 0. In a different case, if the inputs were different, say this is an 8 instead of a 2, now the sum is 2, and so the output of the neuron is 2. And so that's all that these simple artificial neurons do in these models. Now, the main feature of an artificial neural network is that you have a bunch of these artificial neurons and they're arranged in a certain way, which is called the architecture of the neural network. And so the things you can vary in the architecture of a simple neural network are the number of layers. So you can put in the input data, it goes to a first layer of artificial neural networks, artificial neurons, those neurons then feed into another layer of artificial neurons and so on until you finally get to the output of the model. So you can change the number of layers. You can also change the number of neurons in each layer. And so by playing around with those parameters, you change the architecture of the model, and you could get the model to perform better or worse on the task that you're trying to train it on, which in our case, of course, would be putting in the bands from the satellite data as input, and then have that trickle through this network of artificial neurons, and as an output, simply output binary classification of yes or no. So that's what the artificial neural network we want to build will do, but you can use these for many different types of tasks. And when you're training these networks, again, you have to tell the network what you want it to do. And so you have to provide it with a loss function, which tells it what kind of the correct answer is in this case. So we'd be able to tell the network for each example we put in if there was a crop or not. And then that trickles through the network, and the way that the network learns is that it changes the weights. So just like in linear logistic regression, the model is learning those beta values. that connect the inputs to the outputs. The same thing is happening for each individual artificial neural network in these, in each individual artificial neuron in these artificial neural networks. Their weights are getting updated by the data. So the learning algorithm changes these values that represent the connections between different artificial neurons. And through that, the network gets better and better at the task that you've given it and the data that you're training it on. Now, one thing to think about in all machine learning models, but it really comes up especially in artificial neural networks, is that you have to think about overfitting. So if the data that you're looking at has a certain relationship, here you can see by these data points that it's a roughly quadratic relationship between the x and the y variables here. And if you were using, say, linear regression, as we talked about, linear regression can only fit a line, it can't fit a quadratic function, then your model would underfit your data. It would try to approximate this nonlinear quadratic function with just a line. And therefore, it's not going to perform very well. And it's especially not going to perform well if you show it data that's well outside of the distribution that it was trained on. So if you had a new data point that was way down here, this line would really predict something very wrong. If you had a model that could represent a quadratic function and you trained it on this data and it captured that quadratic function, then that would be great. Then it would probably extrapolate pretty well to new data that was put in that it wasn't trained on. It's actually capturing the right relationship. Now you could imagine an even more expressive model that can do more than just a quadratic function. It could actually do this like super squiggly line here, which is doing very well on the training data. It's catching all of these points exactly. It's going through them. But this model is probably not capturing the real underlying relationship in the data. It's overfitting to the training data. And so by overfitting, it won't actually extrapolate well. It will do something crazy if you show it data that it wasn't trained on because it's learned the wrong function. So you want to always be careful about matching the complexity of your model to the complexity of your data, which is hard because you don't always know what the true relationship is. But when you have more expressive models like artificial neural networks, they have all these parameters in them. You can get these really deep architectures. They can learn to fit almost any function. And it's really important that you're not actually overfitting to your training data. So overfitting will cause poor generalization on the test set, as I talked about. And it's a consequence of working with very flexible models that have enough parameters to really try to capture every point in the data set, in the training data set. And so you have to be careful to try to prevent overfitting. And you can do that by controlling different hyperparameters of the model. So different things about perhaps the architecture or the way the model learns. You can vary those things to try to stop it from overfitting to the training data. And of course, when you evaluate on the test data, you'll see if your model is performing poorly on the test data, but is performing well on the training data, that might be because it's overfitting. Okay, so to summarize what you'll be doing, you're going to start by exploring this crops data set. Then you're going to train a logistic regression model to detect crops in the satellite data and evaluate that model on the metrics that we discussed. Then you're going to train a simple artificial neural network to try to also do that same crop detection, and you'll explore the concept of overfitting in that model.